All right, so these are your old properties that you had from logs. Usually in algebra, you probably saw them written with the log, the regular log, instead of the natural log, but they were all still the same properties. It doesn't matter if you're using regular logs or natural logs. We will see the regular logarithm in Calc. However, we see more of the natural logs than any of the others, so usually things are written with that natural log aspect, which just meant for you from the past, just meant that the base was an understood E. That's all that it meant as far as the logarithms are concerned. So you had a regular logarithm that was base 10, or some other number was written as a base, like a base 4, or base 6, something like that. Or you had a natural logarithm that was base E. That's the only difference. So your three main rules, and you had several different ones, but these are all we're really worried about. If you had a product, went to addition. If you had division, went to subtraction. And the way I remember it is a product's just rapid addition anyway. So like your calculators, they don't really do 7 times 9. They add 7 9 times really fast. That's what's happening there. Okay, so, and then division, more that rapid subtraction. If you do 20 divided by 3, it's how many times can you subtract 3 off of 20? So it's really happening there. Then the last one, the powers come to the front. Whatever the exponents are, come to the front. I put this up here just to kind of remind us. This was the point on the graph. So a logarithm graph looks something like this. We don't work a ton with the graphs here just because you have your graphing calculator you can graph, but it goes through the point 1, 0. So that's why the natural log or even the regular log of 1 was 0. All right, so let's kind of look at these, review this a little bit, and then we'll get into the calculus part of it. So what if I said expand? And I had ln x squared y cubed over z to the 4th. So expand, it means I want to separate it into its individual logarithms. So I'd have a log of x, in this case a log of x, a log of y, and I'd have a log of z. So what we want to remember is all the powers are going to come to the front. So the 2 will come to the front of the x one, the 3 in front of the y one, the 4 in front of the z one. I would have 2 ln x plus 3 ln y, because I see a product. Product is plus, then minus 4 ln z. If it's division, it's subtraction. All right, so usually the way I remember it is if it's on the bottom, it's minus. If it's on top, it's plus. Now this is really y. They're really all pluses. I can rewrite this as z to the negative 4. The reason it's subtraction is because you're bringing a negative 4 down. The negative 4 exponent. So this property is really the same as the first one. It just means that b was to the negative 1. That's what brought the negative down. That's why we end up with that piece. Okay? So, that being said, write what you think this one is. Yesterday's? Okay, so on this one, the answer would be, or final answer would be, negative 2 ln A minus 3 ln B. If you wrote natural log of 1, then minus. That's still correct, but natural log of 1 is 0, so I can leave that out. It would be wrong to do that, but that's just going to be a value of 0. Everybody okay there? Okay. What if you had this? ln x squared over e. Yeah?
Sorry, I have one question on the last one. If you did like 2 natural log of a plus 3 natural log of b, but then had it in parentheses with a negative on the
Yes, that would be okay too on this last one. Negative, and you use parentheses.
Yeah.
That's still correct.
Okay.
And that's really what's happening also, is just distributing that negative. But that would also be correct, yeah. Nothing wrong with that. Let's see. What do you think? Where'd the 1 come from? E. That natural log of e is 1. Now, do I expect you to remember that immediately? No, but you've seen that before. That should sound familiar, okay? If you type it into your calculator, you'll get 1. And things like that. So if you wrote 2 ln x minus ln e, then you're using the property correctly. That's fine, but ln of e is 1. And the reason was, when you were working with logs, if the base was the same as what you're taking the log of, that's what's creating the 1. So that's why even back to the past, the log of 10 was 1, because that base was 10. It didn't matter what the log was if the base was the same as what you were taking the log of. Everybody okay there? Or are you okay going back the other way? So put it back, plus would be on top, minus on the bottom. If I go back the other way, I do have a lot of students that once they see that negative exponent, and I don't know if you were shown the negative exponent in the past or not, but a lot of times coming back the other way, I have a lot of students that once they see that, they like doing this, x squared, y cubed, z to the negative 4. Then it's just kind of back to the 1 property. And then you could drop the z down if you want. It is on the bottom, but there's nothing wrong with that negative exponent sitting there. Okay? We do see it go away a lot. We see it left in there a lot of times too. Right, that's for sure. I know back in algebra, most of the time you were told get rid of all the negative exponents. And here you've seen them left and gone. It doesn't matter as long as we understand the difference. Everybody's okay with that? All right. Let's get to new stuff. All right. Those properties are going to come in handy, but here's our new rule. Derivative. Derivative of that natural log. Derivative with respect to x of ln of x is 1 over x. So what's going to happen to us in this unit is we're going to get to a lot of these different specialty functions. And logarithms were one of them. We're going to see a lot of different specialty functions. So our old power rule, product rule, quotient rule, that stuff, it's not going away. They're the same rules. Nothing wrong with that. But now we're going to see some of our specialty functions like a natural log, a regular log, e to a power, things like that we haven't seen yet. So those pieces. Here's our first one. Whatever I'm taking the log of, the derivative is 1 over that value. Now one thing to remember, the chain rule is still at play. We always use the chain rule for derivatives. But let's look at this inside here. The derivative of x is 1. So this would be times 1, which isn't going to change anything. Everybody okay there? So let's look at this. Let's say f of x is ln x squared. So this is where that chain rule will come into play. F prime of x would be 1 over x squared. So 1 over whatever I was taking the log of. Whatever that value is, now times the chain rule, 2x. So we're always applying that chain rule. Which means in this case, an x would cancel, right? Okay, there. So 2 over x. Everybody okay with that? Now, those properties I talked about, I wouldn't use one of those properties here because x squared is a pretty basic function, but let's kind of think about what's happening with those properties. Ln x squared, you could rewrite that as 2ln x if that power came down. Everybody okay with that? So now if you took the derivative, 2 times 1 over x, back to 2 over x. Now, would I do that every time? No, because the chain rule is pretty simple on an x squared. It's not a big deal. But if I had this longer logarithmic piece, which we'll see in a few minutes, maybe I would come back and use one of those properties to make it smaller. Something like that. So that's how I read the properties. They're going to come back into play some for us. So let's go f of x equals 2x ln square root x plus 1. So if I look at that, that would be my old product rule. I have 2x and then times that ln x square root x plus 1. So it's still a product rule. Think of it like, let's see, there's my first, the 2x, there's my second. So our new rule is going to come into play right here when we deal with that guy, but it's still the same old product rule. So the derivative, first, 2x. Derivative of the second, 1 over square root x plus 1 times the derivative of the inside, which is 1/2 x plus 1 to the negative 1/2. Remember the inside, I'm just looking at this piece here. Plus ln square root x plus 1 times derivative of the first, 2. Now we're going to do some simplifying here, but that's the raw form. So I followed my same old product rule. First, 2x. Our new piece, derivative of the second. 1 over what I'm taking the log of. Chain rule, derivative of this piece. 1/2 x plus 1 to the negative 1/2. And finish out the product rule. Second, and then derivative of 2x is 2. Okay there?
Is it possible to use a substitution?
That's integration. So yes, if you're doing substitution, that would be integration. Which, guess what we're doing tomorrow? Integration. It's coming back. All right, so let's see if we can simplify this here. First off, the 2's a cancel. 2 times 1/2, that's gone, right? This could drop to the bottom. And if you did a square root times a square root, you'd actually get just what's inside, x over x plus 1. Plus then 2 ln square root x plus 1. That simplified piece. Okay there? Okay, let's go back to just a basic log. I say a basic log, but it doesn't have a product rule or anything. Let's say ln x cubed minus 2x. So when I'm taking a derivative and I see a logarithm, my thought would simply be 1 over whatever I was taking the log of. So my start would be 1 over x cubed minus 2x. Then the chain rule, derivative of the inside, 3x squared minus 2. Not really anything I can do as far as simplifying here. I could put this value up in the numerator with the 1, but that's really about it. Nothing's going to cancel. Everybody okay there? Okay, all right. Different look here. So I'm going to bring back in that quotient rule. I'm going to say f of x is ln x to the fourth over x squared. Ln x to the fourth over x squared. Now remember, those two can't cancel because one of them's trapped inside the log and the other one's not for that piece. So I go through the quotient rule. Which starts bottom, x squared. Derivative of the top would be 1 over x to the fourth times 4x cubed. There's that chain rule off of that. Minus the top, ln x to the fourth times derivative of the bottom, 2x, all over x squared, squared that bottom squared. Now, just when you're looking at that raw form, follow through the rule. We got to do some simplifying, but just follow through the rule. We did the bottom. Here's our new piece. 1 over x to the 4 times derivative of the inside. And then minus the top. Derivative of the bottom is 2x, bottom squared. Okay, let's clean this up a little bit. Let's see, I'd have a 4. This will be 4 over x. One of them cancels, so that's just 4x. Because up top you'd have 4x to the 5th over x to the 4th. You okay there? Minus. You can leave the 2x on the back end or bring it in front. Usually I'll bring it in front just so I don't have to do the parentheses. Over x to the 4th. And then in this case, I can still take out another x, all three parts. So I'd have 4 minus 2 ln x to the 4th over x cubed. That's a big leap going from here to our final answer part here. But just follow your old rule. This is our old quotient rule. The only thing new for us right now, we're dealing with this part right here, is in there. Other than that, it's the same old quotient rule. Are you okay there? So let's give a different look here. Let's say f of x is ln of the ln of x. Well, definitely not the best looking one. It looks pretty simple, but also looks strange at the same time. You have an ln of an ln. But it definitely looks a little more simplified than this one. We're just not used to seeing two ln's there. Follow your rule. Derivative of a natural log. 1 over whatever's inside the log. So the derivative of a natural log, f prime of x, 1 over whatever's inside. Well, inside's ln x. Then chain rule. Derivative of the inside. In this case, it was 1. In this case, it's 4x cubed. In this case, the inside's 1 is ln x. So the derivative of the inside is 1 over x. Still sticking to that same rule. You can combine them. That's really about it. But you can't make it x squared. I can write x ln x on the bottom. But that's really about it. I guess technically you could do this. 1 over ln x to the x power. But I don't know if that looks any better on something like that. I'd probably leave it like that. Oh, let's go f of x equals ln absolute value sine x. Now, treat it as if the absolute value is not there. What you do? Half divided? Look right, cotangent. Would it be correct to write cosine over sine? Yeah, it's the same thing, right? So, don't care about that.
Is that the absolute value?
It would not be the absolute value. All right, so we'd have cosine over sine, which is cotangent. Now, this is what's happening on the absolute value. Remember your logarithmic graph, you can't take the log of a negative number or 0, right? That would be undefined. I remember the basic log graph that I showed in the beginning. It doesn't comb over here, right? So you can't have a negative inside there. Sine has a chance of being negative. You can take a sine of something and get a negative value. So that's why in the logarithmic piece, we'll have to put the absolute value to ensure it's positive. This is no longer, or either one you look at, is no longer a logarithm. That's why I don't need the absolute value. So when you took the derivative, that's why I said just kind of pretend the absolute value is not there. Work through your process. Because I don't need it in this case. Or if I leave it like this, cosine over sine. But oftentimes with trig functions, we'll see those absolute values come in. All right, your properties that we talked about before. Let's look at this one. Let's say f of x is ln x squared minus 2 cubed over square root 3, that'll be nice, we'll just go 3x cubed. All right, so this would be derivative 1 over this whole big fraction, right? Which actually isn't too bad. But then look at the chain rule. The chain rule would be the quotient rule with that product thrown in. That's when it starts looking ugly, right? This is where the properties can help. If you get a complicated looking logarithm, go through and use the properties. I can rewrite this as ln x plus 3 ln x squared minus 2 minus 1/2 ln 3x cubed. Are you okay with that? Now look at the 3 individual pieces, and those look a lot easier. I'm not going to say it's a nice simple problem, but each individual piece should look easier than this guy. And if I wanted to, I could even split this one up even more. That's a product. But let's look at the derivative here. 1 over x. Plus 3 over x squared minus 2 times 2x for the chain rule. Minus 1/2 1 over 3x cubed times 9x squared for the chain rule. So individually, not quite as bad. This is where the properties can help you. Now we still got to do some cleaning up here. Let's see what I can do. 1 over x plus 6x over x squared minus 2. 3 times 2x. Over here, let's see, x squared and x cubed. That'll cancel out and leave 1x. I'd have minus 3 goes into 9 3 times over 2x. Are you okay with that? Now that's correct, but you've seen at times where, like in the back of the book, they'll have it as a common denominator or something, or in the multiple choice part of the question. This is correct. But just to kind of review, if I went and got a common denominator, it'd be 2x, x squared minus 2, as x goes into 2x. My new numerator would be 1 times 2 times x squared minus 2. 1 times the 2 pieces it didn't have, plus 6x times 2x minus 3 times x squared minus 2. Now a lot of simplifying and combining there, you can see what to do. As far as the simplifying, pretty basic for us. I mean, we know we're going to distribute, combine like terms. I'm not going to say it's easy, but we've seen that many times before. So let's see, that'd be what? 2x squared plus 12x squared is 14x squared minus 3 is 11x squared. That would be negative 4. Positive 6 is plus 2. Unless I messed up there, does that look right? Two, 12, 14 minus 11, negative 4. Everybody agree with that? Now, the goal I want you to see is you don't have to use the properties all the time. But sometimes if we use properties, we can make 2 or 3 individual functions look better than the one big one. And that's the nice part. Okay? That makes the derivatives easier. Yeah, sometimes the simplifying is still a pain. Look at the other way around. If I stuck with this, which I probably would stick with this because I've done so many of it, it doesn't bother me with that long quotient rule. But it can be a pain. If you stuck with it, look at this. It'd be f prime of x, 1 over this whole thing, times, and here comes the quotient rule. Bottom, derivative of the top is a product rule. First, derivative of the second, chain, plus second, derivative of the first. Second derivative of the first, and then minus top, top x squared minus 2 cubed, derivative of the bottom, 1/2, 3x cubed, negative 1/2, 9x squared, all over the bottom squared. And then still have to simplify.
Oh, shit. Yeah, pass.
So I mean that's the, but we didn't do anything new there as far as a rule. We still just follow. I went right through the quotient rule, but you've got a product in the middle and a lot of terms, and it starts getting really ugly fast. Okay, So when you write it out into the three simpler forms, or simplistic forms, those are sometimes easier to take the derivative of. Now, would I use my properties on every single logarithm I see? No. But if I definitely have a complicated one, I would use it, split it up, even if I did have to put it back together. Because dealing with those three individual pieces is a lot of times easier than dealing with this whole thing, as far as what you would have. Especially when you think about careless mistakes, pretty simple to make a careless mistake somewhere in there. It just blows the whole thing up. I'm not saying you wouldn't make a careless mistake on these, but these three individually are probably less likely than that one big one on the careless mistake. And so use them when you see fit. We're going to have those properties keep coming back in on these logarithms and stuff. Use them as you need to, but just remember that they are helpful. They're there to split stuff up for a reason. So the question came in from back in algebra. Why are we working with these properties? Because they make things easier when used. Now you can see one application where it is making things a little bit easier to get it split up. And we'll see the same idea with integration. If I have it split, it kind of works better sometimes than the whole. I can look at some of those different pieces there. Okay. All right, homework. Let's see, 5.1, 19, 21, 29, 37, 41 to 53. Remember, those are odds. 65A, 73.